Brennan, Ireland, and his supervisor is Manuela Campanelli, and I'll invite her to say a few words. Oh, I'm sorry, I forgot the technical stuff. Technical stuff, Manuela's coming here. So there'll be a presentation from Brennan. Please hold your questions. At the end of his presentation, there'll be questions from the audience, and then there'll be a closed session with only his committee where everybody else will leave the room, including the people in cyberspace. And right, okay, so I think then without further ado, Manuela.
Thank you. So it is my pleasure to introduce you Brennan Ireland, soon to be Dr. hopefully Brennan Ireland. And Brennan has been working with me and my colleagues at the CCRG since 2013, and he's been an absolute pleasure to have him in the group. He's not only been an excellent PhD student and researcher, but he is being actively engaged in being a good citizen of the astrophysics community and the center, always offered help whenever there was help needed, either sometimes to even cover classes or to collaborate with individuals in the group, and or giving outreach talks to with other students. So Brennan is a particular talented individual, I would say very well balanced individual who has been very successful so far in the group. And definitely the most elegant among all the students I ever had. So it is with such a pleasure that I will introduce him, and he will be today talking about his journey into the Inspiral binary black holes. In particular, he's going to talk to us about the effects of spins and eccentricity on space-time benefits and gravitational radiation. So if you're wondering what those are, just listen to his talk.
Thank you, Manuela, for that wonderful introduction. Hello, once again, my name is Brennan Ireland, and today I'm going to tell you about the work I've done here at RIT over the past 5 years. So first, I'd like to break down that somewhat cumbersome and confusing title. Just very simply, what do I do? I study the effects of spins and orbital eccentricity on binary black holes in the Inspiral regime. Why do we want to do this? Well, for one, we have detected binary black holes now. In 2015, with the detection GW 150914, 2 binary black holes were seen via the emission of gravitational waves. So it's a very exciting time to be studying this, and there are a lot of very important effects that we have yet to really fully explore. So my work is broken into 2 major project areas. The first, I model the space-time due to binary black holes. And in the second, I study the motion of binary black holes to generate gravitational waves for potential future detections. But before we start, I'd like to give a really quick anecdote. This is now Nobel laureate Ray Weiss. He gave this anecdote at the APS in, this past year, and I really liked it, so I'm stealing it. And the anecdote is this. So the binary black hole detections that we've seen so far are massive, and there's a huge amount of energy that's generated. The first detection alone generated 3 solar masses in energy. It was radiated away via gravitational radiation. So we can ask a question to give you a little bit of physical insight into these kind of systems. What would happen if one merged close to us? I mean really close. What about like 1 AU away from us? So if we put the first detection, which was about a 30 solar mass black hole and a 30 solar mass black hole, they collided, generated 3 solar masses in gravitational wave energy, went out to infinity. What would happen if that was in our neighborhood? What is the physical distance that would be displaced by these gravitational waves passing through? And the answer is a bit surprising. The answer is the physical displacement is only about a micron. So if this incredibly cataclysmic event happened right next to us, we wouldn't feel it. It'd pass right through. I mean, our gravitational wave detectors would pick it up. You may be able to hear it. Your inner ear is pretty sensitive. But as for life on Earth, nothing. Don't make a disaster movie based on this. And so the relativistic two-body problem is the source of these gravitational waves. This is a nice visualization done by Nicole Rosato here at RIT. So now with that little anecdote out of the way, I'm going to strip away all of your physical intuition, and we're going to jump into general relativity. So general relativity uses a kind of an interesting unit system. We use a unit system where we set the universal gravitational constant g and the speed of light c equal to 1, the number. When this happens, you can pull out all of the units in your problem. All the units drop out, and you can express any quantity in terms of one fundamental unit. So you can express it in mass, or distance, or time, any physical quantity. We're physically motivated to do this because we want to treat space and time equally, and we want to treat gravity as curvature. So I'm going to use this unit system for the vast majority of this talk. And if ever you are seeing a number where I say, oh, the distance between the two black holes is 20 m, and you want to know what that is in actual distance units, here's a quick useful conversion system. One solar mass is about 1.5 kilometers. And it's about 5 microseconds. So pick your favorite black hole mass, 10, 100, 10 to the 8, plug it in, and that'll give you the distance. We're also going to be talking about spins. And in this talk, I'm going to use primarily the dimensionless spin parameter. It's related to the physical spin of the black hole by this quantity m squared. So just multiply by the mass squared, and you have the dimensional spin. The dimensionless spin is a nice variable to use because it's bounded between 0 and 1. 0 being a non-spinning black hole, and 1 being the maximal amount of spin allowed. And finally, a quick note is that in general relativity, we like to express the space-time as a metric. This is a way of relating distances between points. And the metric in general relativity is Lorentzian in signature, which means that there is a minus sign on one of the dimensions. All right? You can put the minus sign on time, or you can put the minus sign on space. It will not change your answers physically, but it is a convention that you have to state at the beginning. Otherwise, all of your problems are going to be off by a minus sign somewhere. So we're going to use the pretty standard relativistic metric signature of minus plus plus plus. So time is negative, space is positive. All right, so astrophysically, why do we want to motivate these, right? So how do they form? Well, for stellar mass binary black holes, there are two major formation scenarios that I'm going to focus on today. The first is called the isolated formation scenario. This is where you have a binary star system, two massive binary stars. They both go red giant phase, they both supernova. You have a black hole, and then they form maybe via some common envelope phase, and you end up with a compact binary. The other one, which we'll talk about a lot in the later portions of this talk, is a dynamical formulation in stellar clusters. So if you have a very dense stellar core, you can get three-body interactions between black holes, and that can perturb the binary, and you can drive orbital eccentricity and separation down. And this is going to be very important for us when we want to study processing eccentric systems. Over here we have the binary black holes that we've seen so far, and their characteristic gravitational waveforms here. So what about spins? Why do we care about spins? Well, because everything in nature spins. The Earth spins, the Sun spins, black holes spin, cat spins. You can define them by a nice right-hand rule. So black holes are going to spin generally because everything is going to have some intrinsic angular momentum. When you have an isolated evolution, you expect that the spins are going to be mostly correlated and aligned, right? If you have the binary star system that forms from some disk, it's going to have angular momentum. The star is going to have the same angular momentum. Maybe the supernova is going to kick it a little bit, but overall you expect that they're probably going to be aligned. Of course, for a dynamic formation scenario, you can't say really anything about it. They're going to be distributed however the last interaction between the binary so happens to kick them. So how high can the spins be? For X-ray measurements, it can be up to almost maximal. 1 is the maximum allowed, so it can be almost maximal. For gravitational waves, well, it's a little bit hard to say. The final remnant, the final black hole, has a spin that's pretty well constrained. It's about 0.7. But the individual black holes that merge, LIGO is not very sensitive to these kind of events yet, and they are mostly consistent with 0. And we'll talk a little bit more about that later. But you can have a black hole that's up and a black hole that's down, and that is also consistent with the LIGO measurements. And as I briefly mentioned, there is a distinct population that can be eccentric when you talk about globular clusters, and this will become important in the later parts of the talk. All right, so thus far I've been talking about stellar mass black holes. Stellar mass black holes form pretty much anywhere that you can have stars. There is another type of black hole, though. It's a supermassive black holes, and these reside in the centers of galaxies. And when galaxies interact and merge with one another, you can get supermassive black hole binaries. This is going to be more important for my first project. The key here is that supermassive black hole binaries we expect are going to have stuff around them, gas and dust, that may form an accretion disk, and it may feed into the individual black holes and form mini disks. So whenever you want to model stuff around black holes, supermassive black hole binaries are a more likely candidate to see light from them. This is a simulation and visualization done by Vasily Maris, who's in the crowd here. And this is, again, a simulation that was done at RIT with Nicole Rosado. How do we detect them? Well, we have gravitational wave detectors that can detect them. We have down here, in this far right-hand side of the plot, you see a LIGO 01. That is the LIGO detector that detected the first binary black hole merger. I have a bunch of other sensitivity curves on here. These shaded areas, these are where sources may live. And we need several different detectors, because stellar mass binary black holes live down here on the far end of the frequency band, but massive binary black holes are much lower in frequency, and they're going to be way out of the frequency band of LIGO. So you're going to need other detectors like space-based detectors LISA, which is going to launch hopefully in 20 years. People have been saying that for 20 years. And then finally, at the very, very low end, you can do pulsar timing, where you try and measure the time delays between pulsars to measure a gravitational wave passing through. All right, so let's just take a quick cartoon of what a standard binary black hole in the Inspiral regime looks like. So you have the black holes up here. This is what they're doing. You have the Inspiral, where they're orbiting one another, often in a quasi-circular manner. That doesn't have to be the case. They get closer and closer and closer due to the emission of gravitational radiation. And finally, they get so close to one another that they plunge in together. There's some complicated merger, and then a final black hole rings down to some steady state. Below this, you see the gravitational waves that you would see here on Earth. This is actually a numerical relativity simulation done in light of the first detection. This was from the first paper. And down here on the bottom, you see the separation as the black holes are getting closer together, and their characteristic relative velocity. So the velocity goes up as they wander their way down, until finally they plunge and merge, and there's some big burst of gravitational waves, and then you have a final black hole left over. All right, so just a quick little crash course in the field, and now I'm just going to say a bit about my individual projects. So the first project that I'm going to talk about is constructing an analytic space-time with spin. Why do we want to do that? Well, whenever there are particles around a black hole, like gas or dust or even test particles, light, you need the space-time to be able to tell you how those particles are going to move, what trajectories they're going to have. So we want to use this analytic space-time to study magnetohydrodynamic simulations around spinning black hole binaries in the Inspiral regime. This is important because a lot of the techniques that I use will break down once the black holes become too closely separated. They get below some critical point, all the approximations are no longer really going to work, and you're going to need numerical relativity. And then the second project I'm going to talk about are the post-Newtonian equations of motion with eccentricity and precession. We want to study this because there is quite possibly a distinct population in globular clusters that are eccentric even down into the gravitational wave regime. LIGO does not have anything for this currently, and there's been a few preliminary efforts. So if we want to be able to detect these, we're probably going to need a robust modeling system. Okay, so first project, modeling the spacetime due to binary black holes. Let's zoom in on this little picture that I had. And this is actually probably the perfect slide for discussing this work. I can discuss my entire project on one slide. I didn't do that, but you could. All right, so this cartoon is the whole picture. All right, we have two black holes, black hole 1 and black hole 2. And then around each black hole, you have a spot of the spacetime that you can model, which we call the inner zone. You can model that via black hole perturbation theory. The idea behind this is that the gravity due to the secondary black hole is still important, but it's a very weak contribution. It's a lot like you standing on the Earth right now. Right? If you're standing on the Earth and the moon is above you, you're not really going to feel any lighter because the moon is above you. You're just going to feel the Earth. But the moon is an important perturbation to the Earth's gravity. It creates tides on the Earth. So you can model in these inner zones the space-time of one black hole plus tidal corrections due to the secondary companion. And then there's this cyan circle that I'm going to talk about in a second. And then there's another region, which is called the near zone, or NZ. And this region is characterized by post-Newtonian theory. I'm going to talk a lot more about post-Newtonian theory as we go. Post-Newtonian theory is when the motion of the black holes is sufficiently small enough and gravity is sufficiently weak enough that you can basically expand out in a small parameter, which is the velocity or the curvature. And this works in a regime sufficiently far away from the black holes, but not so far away that you have to start taking into account the fact that it takes time for moving a black hole here to be felt over here. That there's a finite speed of light. And that happens in this zone from here out off the slide. This is called the far zone. This is when retardation effects become important. And this is where you end up with gravitational waves. So we have the inner zone, where we have one black hole with plus tides. We have the near zone, which is the motion and orbit of the two black holes when they're moving slow enough and the gravity is weak enough. And then you have the far zone, where all you see is outgoing gravitational waves. In between these spots, you have these big cyan circles. These are the buffer zones. This is an area in which both solutions are going to be valid, all right? And you can take, and this is kind of the key to this work, you have to have these buffer zones. You can take, in these buffer zones, the solution, the space-time from one, and you can smoothly match it to the space-time from another. We use a procedure called asymptotic matching, and it basically tells you the coordinate transformation that you need to do to go from this space-time to this space-time, and this space-time to this space-time. All right, so post-Newtonian theory. Like I said, it is a weak field, slow motion expansion. This works in the Inspiral only. Once the black holes get too close together, breaks down. Don't use it. It doesn't work. The mathematical requirements is that the characteristic velocity has to be much less than 1, and m over r has to be much less than 1. It's basically a Taylor expansion about these two small parameters. And as we go on, I'm going to mention, because I'm going to say Pn order a lot, that means the power of V over C, or the power of m over r. All right? So an nth Pn order is V over C to the 2n. So if it's V over C squared, that's a 1 Pn effect. All right, so in our space-time project, we use these post-Newtonian terms. The metric is specified out to 2.5 Pn, so V over C to the 5th. And then we have equations that evolve the black holes forward in time. And these equations are specified to 3.5 Pn, so V over C to the 7. And you do get interesting effects that enter at higher and higher post-Newtonian orders. So the spin of an individual black hole will couple with the orbit. That starts at 1.5 pn. The spin of one black hole will couple to the spin of the second black hole at 2 pn. And then dissipation or radiation reaction, the loss of energy due to gravitational waves, will come in at 2.5 pm. So there are important effects that you have to capture at high post-Newtonian orders. If you don't have this, the binary doesn't inspiral ever. So we need these terms. It's just that they can come in at high post-Newtonian effects. We use these equations of motion. Basically, this is evolving the phase of the binary, where the binary is in time, and it's a frequency variable, the velocity frequency variable v. And we can solve these by expanding out these terms in higher and higher post-Newtonian terms, and then solving directly or numerically from here. So this work was an extension of some work that was done before I got here with a non-spinning spacetime. And when you go from a non-spinning spacetime to a spin spacetime, a lot of things can change. In the metric, the inner zone is a completely different formalism. The formalism used for the non-spinning was Reggie Wheeler. This works really well when you have spherical symmetry. And that's fine when you have a non-spinning black hole. There is no preferred direction. You can just take the black hole and rotate it around, and it's the same black hole. But when you have a spinning black hole, there is a preferred direction. It's the spin direction. So if I rotate the black hole, I have a physically different situation than here, because the spin direction has changed. You can solve this with Tucholsky, the Tucholsky formalism. It's basically a very clever way around this problem, and you expand out in a particular basis. In the near zone, you pick up a bunch of spin-dependent terms, all the way up to 2.5 pn. So we get all spin terms up to that. And then in the far zone, you pick up more multipole moments, and this is how you solve for the gravitational waves, is via the binaries, quadrupole, and octupole moments. So we pick up more spin-dependent multipole moments up to octupole. And then the equations of motion, and this is a somewhat subtle point that I'll come back to a little bit later, is that you do have 3.5 pn, but it's 3.5 pn beyond the leading order. So you pick up a bunch of spin-dependent terms that are actually a higher post-Newtonian order than is technically 3.5 pn. And I'm going to come back and touch on this in just a bit. Okay, so we've done this procedure now. We have the inner zone, and we've matched it to the near zone, and then we have the near zone, we matched it to the far zone, and we have a complete spacetime, a whole picture. And the first question that you can ask, and a natural one at that, is how well did you do, right? What can you say about the spacetime quantitatively? And for this, we turn to the Einstein equations. So these are the Einstein field equations written out generally. This is the gravity, the curvature of the spacetime here. And over here, this is all the matter, the stuff around it. When you have a binary black hole spacetime, this matter component is 0. And that gives you a really nifty way to compare the spacetime quantitatively. And that is that there is a particular quantity invariant, we call it the Ricci scalar. And this invariant will be 0 for an exact solution to the Einstein field equations. It does not matter what the solution is. If it is an exact solution, R will be equal to 0. So we can ask, how well have we done by calculating the Ricci scalar and seeing how far we are from 0. So that's what we do. I'm going to spend a little bit of time explaining this plot. It's a bit complicated. So what we have here is plotted on the y-axis is the absolute value of the Ricci scalar, the magnitude of the Ricci scalar. And on the x-axis, we have the distance. It's the x-axis distance. It's basically the radial distance between the black holes. So this is 0. This is in between the two black holes. The black hole is located at 10 m. And all of these green dashed dotted lines denote the boundaries, the boundary layers. So what we have right here, this one that's really close to that black solid line, that is the inner zone. It's this big. It's very, very, very small. And then right here, this big chunk, this is the buffer zone between the inner zone and the near zone. So this is where we stitch the inner zone to the near zone. And then we have the near zone here, then we have the buffer zone, and then finally the far zone. And what you can see, and I'm going to zoom in on the little bit around the black hole in just a second, but what you can see is broadly, the largest discrepancy that we're getting is in this buffer region. And we expect this because when you are doing an asymptotic matching, you're not being exactly correct, right? You have to take the inner zone solution maybe a little further than it should go. To take the near zone solution maybe a little further you can go, and you have to match it in some pretty complicated procedure. But you can see that it's smooth, and that the spin values, changing the spin values, so these are the different colored lines, doesn't dramatically affect the Ricci scalar. And this is really good because remember the non-spinning binary spacetime had already been calculated, and that's this black line. So we're not doing much worse than the non-spinning case. All right, now we can zoom in, and here I have drawn a couple more lines that are very important. The first is this solid blue line. This is the innermost stable circular orbit. Right? This is incredibly important when you're talking about gas dynamics. When you have particles around black holes, this is the point of no return. If they come in here, they are either going into the black hole or they are leaving the system. So this is kind of the relevant surface for MHD simulations. This gray dashed line, this is the actual horizon. This is if something comes in, it is never coming out. And what we see is that we do have a larger violation between the ISCO and the horizon. Right? And it does get pretty big, like 10 to the minus 1-ish for a highly spinning aligned case. But because we're using this spacetime primarily right now for MHD simulations, and the ISCO is the important quantity, we're well below these big buffer zone humps. All right, so this was one little type of simulation you can do where you have the black holes and then you have the spins aligned and you go low spin, medium spin, and high spin. The other scenario that you can talk about is if the black holes are anti-aligned, like this, like this, or like this. And that is these. So we have, again, black is non-spinning. This red dotted line is highly spinning and aligned. This was shown on the previous plot. And then the blue dashed line is this situation. And the cyan line is this one. All right? And you can see that changing the spin values, while quantitatively it does shift and grow the violation just a little bit, qualitatively it's still very much very similar. So we're saying here that we have a good spacetime that's incorporated spin, and we're not doing significantly worse than the non-spinning spacetime. All right, so this is a great way to measure it, and it's a good first step. But you can ask, well, what is an acceptable value of the Ricci scalar R? Does it have to be 10 to the minus 5? Can it be 10 to the minus 2? And the answer is that it's not terribly clear with that measure, because you know that 10 to the minus 3 is smaller than 10 to the minus 2, but is larger than 10 to the minus 4. And that's all you can really say. How close is it to 0? You want it to be as close as possible. So we can come up with another invariant quantity, and this time we use the Kretschmann invariant. This is the Kretschmann scalar in general relativity, and the important thing is that this is non-zero, this is non-zero, and for a vacuum solution, for black hole solutions, this is 0 and this is 0. So you can normalize your invariant. You can normalize your invariant by taking the thing that should be 0 and dividing it by the total. And this will give you some kind of like relative comparison of the spacetime. So this is what it looks like. Again, you see these two big buffer zone humps, but it doesn't really get above 0.01, which is good. You see that it does very well when you get close to the black hole. And then there is kind of this really strange behavior where it gets big as you go further and further away. And this is surprising because in the Ricci scalar plots, this was the best area, right? This was the area that was the lowest. So what's going on? Why is it bad now? And the answer is really our choice of normalization. So the number that we're dividing by is this Kretschmann scalar, and it drops off very, very fast in the far zone. All right? And if you imagine schematically that the far zone metric goes as something that has error, h mu nu, these are the multipole moments that you can get, that you can successively iterate further and further out, but you have to truncate at some finite number. It drops off as 1 over r, which is good, so it should damp out. Those error terms should get smaller. But when you're dividing by something that approaches 10 to the r to the 6th, 1 over r to the 6th, dividing that is going to give a big growth. So we're comfortable with this. We say that, yes, we know that the behavior in the far zone is bad, but if you want to look at far zone behavior, it's probably better to just look at the Ricci scalar. All right, so really quickly, I'm going to talk about the second thing that you can do with this, which is, okay, great, so I've constructed a spacetime. The spacetime is valid, as we've shown, and you can evolve it so the black holes can orbit. But now I'm going to ask a question that seems very simple and turns out to be very difficult, which is, I'm going to take the black holes like this. Now what about this situation? Just make them not perfectly aligned with the angular momentum. If I just bump the alignment slightly, what happens? So to explore this, we can write the spin of one black hole as some rotation angle from a simple Kerr solution with the spin pointed along the z-axis. These are Euler angle rotations, essentially. So you can take it, and you can take with these two angles, you can rotate it to another orientation. And then you can take the inverse transformation of that and say, alternatively, if I have it and it's pointed this way, I can apply this rotation operator to take it to this. The good news about having the black hole pointed directly up is that we already know how to solve that problem. We've done that in the spin project that we did. So if we can rotate it, and we can apply the matching to the rotated solution, and then we can rotate it back, that will give us a lower order, but still valid matching condition, which allows you to match to the spacetime. So this was a small paper that I wrote with Hiroyuki Nakano and Manuela and Eric West in 2016. And we showed that, demonstrated mathematically that yes, you can do this. And then we moved on because if you want to actually evolve this system, you're going to need to know how the equations of motion work. And that's what we're going to get to shortly. So wrapping up this project briefly, the benefits of this work, we constructed a new fully analytic spacetime with spin. This is important if you want to study gas dynamics around binary black holes. We recovered a bunch of known spin effects. I didn't show it in this presentation, but you can recover things like the orbital hang-up effect, where the binary due to the spins actually spends longer in the Inspiral regime. Our analysis with the Ricci scalar and the relative Kretschmann show that our metric is valid at any time, and we can evolve the spacetime forward in time to also show that we have a valid spacetime. All right, so now I'm going to jump. Let's talk about the motion of binary black holes for the purpose of generating gravitational waves. Right? So I said I'd talk about eccentric binaries in a bit, and here we are. So there is, with recent globular cluster simulations, people who take 1,000 or 10,000 stars and evolve them forward, and you put in a bunch of physics like supernova rates and all that stuff, you can end up with a population of black holes that form binaries. And then you can evolve those binaries forward, and you can ask, what is the eccentricity when you get to the LIGO band? And what you find is that there is a pretty distinct population that has a high eccentricity. This is an eccentricity of 0.1. To give you a physical intuition, Earth's eccentricity is like 0.03 or 0.01, something like that. So this is significantly higher than the Earth-Sun system. But it's still, this is really high for binary black holes. This is enough to change the signature that we would see in the detector. So I want to study this now. I want to see what are the implications. So what we're going to study is this distinct minority of binaries that end up eccentric in the LIGO band. It's about like 3 to 5%, but this is still enough that we are going to see this eventually when we get higher and higher sensitivities in our third observation run and beyond into third generation gravitational wave detectors. So I'm going to pull from just kind of the bulk of the distribution as well. So we're focused on lower mass binaries, binaries that are about like the ones we've seen so far, just with eccentricity. And what about spins? Well, we are going to pull as well from black holes that have some low to moderately low spins. All right. This is a plot of the spin distribution via mass. This is the birth spin. Chi b is the birth spin. This is whatever spin the black hole has with the last dynamical thing that happened to it, right? This could be the supernova that imparted a spin to it. This could be the last black hole merger that it underwent that gave it a spin. So I'm picking a moderate birth spin of about 0.2. And then this is the effective spin that you get out of it. Effective spin, this is what LIGO measures. It's basically the mass-weighted spin projected along the orbital angular momentum. All right, so it says, of the total spin, chi1 plus chi2, weighted by the masses, what component of that is along L? All right. So I'm going to pick something that is, moderately low chi effective. And all of this states that we're going to need something that can handle an eccentric binary and an eccentric precessing binary. So I'm going to do that now. I am using the direct equations of motion, the direct integration approach in post-Newtonian theory. You can explain it schematically like this. So you have the acceleration due to the two black holes. There's going to be a component. That's the non-spinning component. There's going to be a component that is the spins coupling to the orbit. There's going to be a component of the spin coupling to the spin. There's going to be a component of the spin-spin coupling to the spin. And then you can just keep carrying this on out. You can take this schematic argument and you can rearrange it into something that's a little bit more intuitive to use, where you have, say, the acceleration looks like gm over r squared times 1. This is good. So this is a Newtonian potential. This is a Newtonian orbit. And then you add post-Newtonian terms A, and then there are terms that scale with the velocity, and then there are terms that scale with the combinations of the spins. And what you end up with are 12 coupled ODEs. All right, you end up with 12 coupled ordinary differential equations for the trajectories and the velocities of the black holes, and then the spins. So here's where all the terms are located. We're using center of mass variables, just kind of say the disclaimers, and that we're also consistent with implementations that have done this as well. So what do these post-Newtonian terms actually look like? Right? So I'm going to show you this is A. This is actually just part of A. This is the non-spinning part of A. And then you add spin terms, and then you add spin terms, and then you add the B terms and the C terms. And so it gets very, very large. But luckily, we can just evolve this numerically. It's not a problem. And then we want to compare it, right? We have an implementation. We say this is great, awesome, but that's how are you going to say that you're doing something correct if you can't compare it? So we're going to take another post-Newtonian method. We're going to try and compare directly to it. This is the Taylor-T methods. This is the equations of motion that we used for the analytic spacetime project. And basically what you can do is you can take the flux due to gravitational waves, and you can expand that out in a post-Newtonian series. And then you can take the energy and expand it out and its derivative in terms of the post-Newtonian series. And then you can evolve these two equations. All right? But if you expand this term, this flux term, out in a post-Newtonian series to 3.5 pn, which is what we want to work to, earlier I said that the flux starts at 2.5 pn. So 2.5 plus 3.5 is 6. 6 pn is the total pn order of this top term. And we don't want to be way higher than our approximation. We want to try and compare as apples to apples as possible. So what we're going to do for the T4 is we need to cut the flux terms to just the leading and then next to leading order. This method, by the way, is you take this rational fraction and then you re-expand that out, and then you can numerically integrate. And that's basically what we're going to do when we compare. Of course, the direct EOM also is not quite consistent with T4 because the direct EOM has no restrictions on eccentricity. And if you miss in your initial conditions just slightly, what that's going to manifest as is an eccentric orbit, a slightly eccentric orbit. Taylor T4 has no eccentricity. It is assumed to be 0. So for the EOM, we need to have an eccentricity remover to get rid of it and damp it down. So that's what this is. When we want a quasi-circular orbit, we need to be very careful with the initial conditions. And what we can do is we can give it the best initial conditions guess that we can, and then evolve it and say, okay, well, how eccentric are you? And you can do that by plotting dr dt, and you're going to see a small wiggle, right? And you can fit dr dt to a part that looks like an inspiral and a part that looks like an oscillation. And then you can remove the oscillation bit, feed those initial conditions back, and rerun it. And then ask, okay, what part looks like an oscillation and what part looks like an inspiral? And you can do this and iterate it down. Here I've shown 3 eccentricity removal steps. You can see that we're stepping down in residual each time. Okay, so great, we've done that now, and we want to have something to compare to. So what is a good thing to compare? The first thing that we can compare to is the orbital frequency of the binary. The orbital frequency is a nice quantity because it's physical. It's a physically observable thing. Right? This is how fast binaries orbiting each other. And we can create a scaling to show the post-Newtonian orders of the orbital frequency. Right? So what you can do is there is a PN expansion for the orbital frequency that looks like the Newtonian orbital frequency plus corrections out to 3pn. You can subtract the 3pn from the 0pn, and the leading order correction should be 1pn. And if you plot that as a function of distance, you can measure the slope on that and ask, does it look like it's 1pn? A 1pn term looks like m over r to the 1. And when we do that and ask, what's the slope, we get something that's pretty close to -1. And then you can repeat this process and say, okay, well, what about this line? What about the 2pn error? You can do that and find something that's really close to -2. And then you can say, okay, well, what about the 3pn error? And here you see something a bit weird. You see a 0 crossing, right? This is due to our choice of gauge. This comes up because there's a log term, there's a natural log term. It's not an issue, We just have to know that it's there, and we can shift it around with our gauge fixing condition. The purple dots that are here too, this is another way to measure the orbital frequency, right? This is saying, all right, well, I have an expansion that looks like the orbital frequency. What if I just directly calculate it with my variables that I've evolved? Does this lie below the 3pn line? And outside of where you get this zero crossing, you can say, yeah, it pretty much does. So when we compare, we can use either the orbital frequency that we calculate or a PN expansion. And then when we compare finally to T4, we see that it is much stronger than a 3pn error, and it scales really sharply with distance. Okay, what's the next thing you want to do? Well, we want to do gravitational waves. So let's make some waveforms. The first thing that you have to do with a gravitational wave is you need to choose a basis, all right? We're no longer just like sitting there looking at the binary. Now we have a detector on Earth, and the binary isn't, you know, in some abstract space. It's there, right? And how is it oriented with respect to us? How is it inclined? So we have to pick a set of detector bases, and place the binary on the detector, right? For this, I picked basically the easiest thing that you can do, which is say, okay, well, let's just say that the binary is directly above us, and it's face on, so we're looking straight down at it, right? You can rotate it with the inclination of the binary. This is the direction to the observer, and these are your two detector basis functions. And then you can calculate gravitational waves. This is the quadrupole formula for a gravitational wave. Gravitational waves can be deconstructed into two independent polarizations and then projected, this operator right here, this is a projection operator, onto the detector basis. And then we can do better, and we have higher order terms that we used for the actual analysis that we coded up to 2pn. Okay, and then you say, well, how do you know how well you did? And what we do here is we construct an overlap. Now, an overlap is basically asking how well do these two line up? And the human eye is actually pretty good at seeing this kind of thing. You can see that these lie pretty much right on top of each other. But if you want to try and do this mathematically, you can construct an inner product space between the two. And then you can take these waveforms and shift them, maximize over that shift, and normalize to get a number between 0 and 1. So this is what a non-spinning binary looks like, and a spin aligned of 0.3. And here we have an overlap of about 0.995, and here the overlap's about 0.98. So we did a lot more than just that. Here are, okay, so two plots. One is the initial separation versus the mass ratio. And the second one is the spins of the two black holes on the x-axis, and the size of the dots are the initial separations. So on the right, your right, my left, on the right-hand side, we increase in initial separation, and then increase in mass ratio, going from 1 to 2 to 10 to 100. And then what we plot in the green color bar is, this is the negative log of 1 minus the overlap, which is basically the number of 9s that there are in the formula. So something that's 10 to the 2 is 0.99, 10 to the 6 is 0.999999, and et cetera, all the way up. And what we see is as we go further out in separation, the overlap gets much better. And as we go up in mass ratio, the overlap gets much better. And this is generally consistent with what we saw in the frequency analysis as well. Then we go to the left-hand side. This is the spin of black hole 1 and the spin of black hole 2. This is black hole 1 is up. This is making black hole 2 minus the same rate. This is holding chi effective equal to 0. We did this just for q equals 1, because we saw that q equals 1 here was the worst overlap that we got. So at q equals 1, this is holding chi effective to 0. And then when you increase chi effective, it gets worse. but as you can see, as we go further out in distance, the small points are 100M. As we go out in distance, the overlap gets much better. Okay. So now we want to talk about an actual eccentricity. And we have to be pretty careful with how we define eccentricity. In GR, eccentricity is not terribly well defined. And there are many different definitions that can give you different results. So here are, this is something that I ran with my equations of motion code. And you can reproduce two different results just based on what you use as the eccentricity definition. So the top one, which is the blue curve here, this is the Newtonian Runge lens vector. This is how you would define eccentricity in a Newtonian sense. And you can see that you end up with a growth away from 0 as the binary evolves. You can do another thing too, which is you can say, let's use something from numerical relativity, which is taking the amplitude of r squared r double dot, and ask how well that does. And you see this oscillates right around 0 for the entire time, right up until you get to the end. This end ended right around 6M. This is important to know because about 5M is when you're going to start plunging. So eccentricity is going to start breaking down there because you're no longer really in an orbit. You're more in a radial trajectory. So when we want to do eccentricity definitions, when we have low eccentricity, we want to use the one that is going to give us the best result. Now, when we have high eccentricities, we can use a geometric definition that works all right, which is you take the maximum distance between separation minus the minimum distance between the two black holes and divide that by Rmax plus Rmin. And that gives you a nice, it's a ballpark kind of number, but it works pretty well to give you an idea of how the eccentricity is evolving. Okay, so let's run a binary black hole. It's a fiducial case. So this is a simulation that I did where I set the initial periastron passage, so this is the closest the black holes get to one another, at 35M. I set the initial eccentricity to be 0.4, so moderately eccentric. The mass ratio was 3/2, so in this case, for the waveforms I set, the first one is going to be 15 solar masses, and the secondary is 10. And then the spin configuration I set so that it's low, a low chi effective, but still within that distribution. And I set one of them to be up like this, and one of them to be like this. So they're 90 degrees out of phase, I guess, with each other. And that is going to create a lot of precession. And then what I'm plotting here are the x, y, and z components of the trajectory. So you can see that there is an eccentricity because it goes up and then down. This oscillation is due to the eccentricity. You can see an inspiral because the apastron distance, the maximum distance up here, is shrinking. And then you see that the orbital plane itself is starting to move around. This is due to the spin orbit and spin-spin couplings of the binary. Well, what do the waveforms look like? Well, so here is one of the polarizations, one of the independent polarizations. For this, I wanted to dimensionalize the units again. So now we're looking at time in seconds, because that's what you're going to measure in a detector. And you're measuring strain, which is basically the change in length over the length. And so I gave it the total mass of 25. So mass 1 is 15, mass 2 is 10. The distance to the source is set to be 500 megaparsecs. And the initial orientation of the binary is directly above us and face on. All right. And here you can see a lot of very interesting dynamics that are present in this waveform that you don't see in that first little cartoon, which is on non-spinning or spin-aligned waveform. You see the effects due to the eccentricity, and you see effects due to precession that modulate the top. So let's zoom in real quick. All right, so zoomed into the waveform at the beginning and the waveform at the end, you see that there are two pretty distinct frequencies. So this is the app-astron frequency. Initially, it's set to about 3 hertz, so this is pretty far below what LIGO is going to see. And at the end, the app-astron has shrunk because the primary burst of gravitational waves happens at periastron, means the majority of the energy is lost at periastron, which shrinks the distance, the app-astron distance, as it closes in. So you're radiating away the eccentricity here. The periastron frequency starts at about 17 and ends at about 15. And then finally, so I should say this is rather optimistically within the LIGO band. I think kind of canonically right now it's about like 30 hertz is the kind of the low end range. We could push this a bit, so 17 isn't completely out, but so this is kind of the low end of the LIGO band, optimistically. And then on top of it, modulating the peaks, you see another frequency, and this is very roughly about 0.1 hertz. This is the spin modulation of the binary, and this is far out of the LIGO band, but this may be picked up if it's strong enough in something like LISA, or just LIGO if that ever gets made, which it's not. Don't hold your breath for that one. So here what we've created with this binary is we've created a multi-band gravitational waveform. We've created a source that spans multiple bands that we need multiple detectors to really study. We have a LIGO source at periastron, a LIGO/Kagra source at app-astron. Kagra will also see it at periastron. And then a DeCigo or LISA source, which to really see that low frequency spin precession. This formalism that I went over, though, is fully generic, so you can scale this up to other detectors. If you want to do like a LISA source, you can scale up the masses. And this is really filling in valuable parameter space that we haven't really touched on before. This does have its limitations. The big limitation is when PM breaks down, right? If ever the binaries become sufficiently close together that we're no longer slow motion or weak field, then you can't use this, right? This is going to happen when you get to really close separations, or if you have something that's so eccentric, you're basically plunging straight in. Right? If it's super, super eccentric, it's going to come around, it's going to hit the black hole, and it's just going to inspiral immediately. So, and the last, I'm over time already, oops. So in the last few seconds, I'm going to just say some of the future work that you can do. The analytic space-time with spin can be extended. You can use the matching procedure. You can extend that to higher and higher orders. That will help regulate that violation that you see in the buffer zones. You can integrate the equations of motion that I just talked about for spin precession into the precessing binary space-time at this point. And then for the spinning eccentric binary, there are a lot of other waveform models that you can compare to. You can compare to other LIGO waveform models. You can compare directly to numerical relativity. You can also think about hybridizing with numerical relativity, where numerical relativity works really well when the black holes are really closely separated. It's pretty expensive and can't be taken a really long time. This method is relatively cheap, but breaks down quickly. So if you can kind of stitch them together, you can create a full waveform for the LIGO detector to use. And of course, our final goal here is that we want to have a spinning precessing waveform. So I'd like to thank everybody for listening. If you have any questions, I'll take them now.
Right, so now we have a small amount of time for brief questions from the audience before the closed session with the community.
I think, I'm sorry, I went over time. I think we have this room until 3, just heads up. So. Well, I mean, then you have no time to deliberate. But.
Well,
yes?
so on slide 19, you have the repeat scalar plots.
Yes.
It looked like the negative aligned spin was different than the positive aligned spin for the curves themselves.
This one?
Yeah.
Yeah.
Why is that? I don't.
Because the orbital hang-up effect works in reverse in that case. So when you have an aligned binary, the spin angular momentum adds to the orbital angular momentum, and you have to, basically what you're having to do is radiate away more angular momentum out of the binary system. When you have it misaligned, L is still this way. When you have it misaligned, you have to radiate away less total angular momentum, and so the binary will inspiral faster. So that's probably why you're seeing that shift.
Let's see, Zach.
Yeah.
Yeah, okay. So you spent a lot of time talking about the analytic metric and its error and trying to quantify, how big the error is. And okay, did you compare though with numerical relativity initial data, for example? And what are these quantities for numerical relativity? Obviously, you would hope that they would be really low because you're solving a much more sophisticated system.
Yes, I don't know that I have a slide, but I do also do the Hamiltonian and momentum constraints as well.
And did you compare with the numerical relativity?
So
there is a paper actually, Josef, you were the first author on, so you might actually comment on that. I don't think Brennan was part of that study, but that's where we took the comparisons with numerical relativity of the space-time.
that was 2013, I think, 2012. I do not remember. Yeah. Yes, you can definitely do this. We can talk about that later if you want. We can, yeah.
And you two can talk about it on the way back during the process. Mark, you have a question?
Yeah. So my question has to do with the accuracy of the analytic space-time near the horizon. So it's true if you're studying accretion that the ISCO is very important, and that may give you a good rough handle on how the disks would evolve. But if you're including spin, then the main interest would be jets, and there the horizon scale physics has to be right? So,
yes.
Or it has to be at least close to right. So, are there some windows into how one could improve the accuracy there, or do you just have to go to numerical relativity?
Yeah. So one of the things that you can try to do to push the accuracy close to the black holes, which is actually a project that I did for a few months here as well, is you can try to do some resummation procedures with the metric. And that's to really try to push the error down as much as possible, as close as you can to the black holes. They were not terribly successful, at least with just trying to use PN. So the idea was to just cheat out the inner zone completely, but using the matching to the inner zone with a resummed PN spacetime, you could probably push it a little ways.
The buffer zone is very close. Is there a way to push the buffer zone further out and get accuracy by just...
So yes, you very quickly run into a trade-off game because the buffer zone has to be where both of the solutions are valid.
Yeah.
So if the buffer zone is too close to the near zone, the inner zone is really broken at that point. And if you push it too close into the black hole, then the near zone's not going to have any real weight anymore, and it's going to be really broken. And you can do a lot. You can play